Okay, thank you, and I'd like to thank the organizers for this very nice conference. So this is a joint work with Niccolò Cesabianchi, Pierre Gaillard, and Claudio Gentile about algorithmic chaining and the role of partial feedback in online non-parametric learning. So the setting is online non-parametric contextual learning. So you have at every round an environment that first reveals a context vector, xt, in the unit d-dimensional hypercube. Then the learner chooses an action yd hat in 0, 1, and gets a loss, suffers a loss, lt of yd hat, and then gets some feedback. The feedback can be, depending on the setting, be instantaneous loss, lt of yd hat in the bandit setting, or what we call the one-sided full information feedback, which is lt of y for all y larger than yd hat. I'll give an example in the next slide. Or the loss function, or the loss function itself in the full information setting. As usual, the goal is to mimic the best function f in some set f. So we have a slightly more general setting, but here I will only speak about the set f of one Lipschitz functions from 0, 1d to 0, 1 for some given norms. And we want to minimize the regrets, which is the difference between the cumulative loss of a learner and the cumulative loss of the best function f in your big set f. As for the assumptions, the sequence of the context vectors xt's and loss functions lt's is arbitrary and fixed at the beginning of the game, and we assume that the losses lt's are either Lipschitz or what we call semi-Lipschitz. So let me give a very brief example of what we called a one-sided full information feedback. So I won't even give you the whole definition of what is second price auctions with reserve price, but let me just comment on the picture. So we have here the revenue of a seller at a second price auction as a function of the reserve price she chooses. Here we have the second highest bid and the highest bid. If the reserve price is chosen in between the second highest bid and the highest bid, this is good for the seller. But if the reserve price is chosen too big, then the revenue is 0. And in this particular context, it's pretty easy to check that if the seller not only observes the own revenue at the end of the auction, but also the value of the highest bid, then she can actually compute the value of all the rewards, or the losses, when turned into losses for any action y larger than yd hat. So we are in a particular setting where we have one-sided full information feedback. Okay. So because of time, I will only comment on one particular context and then very briefly extend to the other types of feedback. So let's talk about full information. So the learner observes the whole loss function at the end of round t. And in this setting, a very natural yet suboptimal approach is to discretize the set f of one Lipschitz functions. So if you want to discretize it with precision epsilon, it's quite straightforward to check that you need very approximately 2 to the 1 over epsilon to the d functions, which I call n epsilon. And if we use those n epsilon functions as experts with your favorite mixture algorithm like hedge, then we can have a regret that scales as the square root of t times the log of the number of experts plus an approximation term, t epsilon, if the LTs are Lipschitz or semi-Lipschitz. By semi-Lipschitz, I mean the loss does not increase too much when you go to one particular direction, which was the case for second price auctions. And if you optimize in epsilon, then you get this rate, t to the d plus 1 over d plus 2, which is a non-trivial regret bound, but which is suboptimal. And the intuition behind this is that here we treat all the experts, which are functions in the discretization, as uncorrelated experts, which is actually a bit pessimistic and harmful when the set f is large, which is the case here. So we follow the less pessimistic approach using the so-called chaining technique. The chaining technique consists in not only using one discretization, but a hierarchy of discretizations. So the level m discretization is an approximation of f at precision 2 to the minus m. And we connect all the nodes at level m with the nodes at level m minus 1 by projecting them on the discretization above. So doing so, we build a tree where all the nodes are labeled by functions in several discretizations. And the way we construct our algorithm is by keeping the leaves as such. So we have functions, and we replace the functions on the internal nodes by instances of the edge algorithm. So any instance of the edge algorithm uses its own children as experts, who use their own children as experts, and so on, down to the leaves. And doing so, on each edge instance, we have an algorithm that competes with its children and whose regret scales as the effective range of its children's losses, which very crucially is proportional to 2 to the minus n. So this is a local regret bound. And if we sum up those local regret bounds from the root of a tree down to any leaf of a tree, then we get this type of regret bound. And if we do the computations, we get a regret up to log factors, which is square root of t for a context dimension d equal to 1 or 2, or t to the d minus 1 over d for context dimensions d larger than 3. So maybe you recognized the well-known upper bound by Racklin et al. In 2015, which was obtained in a non-constructive manner. So here we got it through an algorithmic approach. It matches the lower bound of Hasan and Megiddo in 2007, so this is worst case optimal in this situation. And this algorithmic approach via chaining generalizes that of Cesar Bianchi and Lugosi in 1999 and that of Pierre Gaillard and myself in 2015, but now to non-convex Lipschitz losses. And quite importantly, we can actually implement a variant of this hierarchical algorithm in polynomial time. So this is a bit more sophisticated, but still the same idea applies. Okay, let me now very briefly comment on what we can or cannot do for other types of feedbacks. So for Bernit feedback, the bad news is that it is in general impossible to derive regret bounds that scale as the effective range of the arms losses. So we actually proved this negative results with Thor Latimore last year at NIPS. So in general, the only regret bounds we have are straightforward bounds. So for Lipschitz or even semi-Lipschitz losses, we have t to the d plus 2 over d plus 3, which was also known in the work of Slifkins, for example. And if we have convex Lipschitz losses, then we can use the convex bandit results to get t to the d plus 1 over d plus 2. However, for the one-sided full information feedback, which is a much stronger form of feedback, closer to full information, actually in between bandit and full information, we can use this stronger feedback together with the Lipschitzness of the losses to derive regret bounds that scale as the effective range of the arms losses through a variant of XP4. And if we replace the hedge instances on the nodes with XP4 instances, then we get regret bounds that are in between bandit rates and full information rates. So these are this one or even this one if we use an additional penalization trick. Okay, so I'm done. Here is a summary of the results, and we will be happy to comment on them at the poster session. Thank you.
So we have time for a few questions before the open problem session. Are there any?
Can you use this hierarchical algorithm as mere descent with a certain regularizer?
So you have to rephrase it.
Okay, so is it like, can I reformulate this algorithm as a particular case of near descent with some regularizer? So hedge can be indeed reformulated as such, but the thing is that at every level we use a different learning rate, so different step size actually. Sorry? So maybe we could reformulate it as such, but then with different learning rates. So somehow we learn very roughly which is the best region in the function space, and then once we get our rough best region, then we look in deeper details and learn more quickly how to refine our knowledge of function space and so on. So we need different learning rates at different levels.
So what is the learning rate? Because
So it depends on the effective range of these losses. So it depends on 2 to the minus m. So this is like 1 over square root of t, but with this scaling factor in front of it. And it also depends on the metric entropy of this set as the number of experts.
Okay, well, we have to thank again both the speakers.